All right. So thank you. Try to figure out this light. I gave a version of this talk earlier this year at SRECon, and part of the feedback I got about it was about the title. So I decided to make it a longer title for tonight. Part of what bummed me out about giving the talk at that conference, I'm gonna stand over there, sorry, was that the audience, I sort of had to gloss over the ClickHouse stuff. So tonight, running on ClickHouse because I want to talk a little bit more about the data store we're using, how that setup works. But I will talk about the concurrency control that we've been able to put in front of our ClickHouse cluster to make everybody run happier and healthier. So yeah, Patrick talked about this a little bit already, but it just for context, right? A big thing that we do at Klaviyo is we send a lot of email. We send a lot of messaging. And we get all that data back. So data from messages we send out using that segmentation engine to be really targeted. Third-party integrations like e-commerce stores feed us their data. And we integrate all that data and provide analytics on it. We give access to that via dashboards, APIs, offline reporting, and we're trying to answer business-focused questions about that data. Who clicked on my email? Where are my customers located? How are we doing sort of mapping revenue to the communication channels? So the team I work on works with providing access to those data stores and to that data. And I'm going to talk to you about the query services that support that. So one way I like to describe it, and I know, I guess, not everybody else is a fan of this picture, but I think about this, right? All these converging data sources, all of these different converging schemas with some common keys that are threaded throughout. We run analytics over them on one giant shared calculator. So our API requests come in, the UI requests to load that data, our offline reporting. We're generating our metrics for those from a centralized data store. So what gets interesting about that, right? There's potential efficiency, but there's also a lot of potential contention. We're going to talk about that. For a little bit of a sense of the volume that we're talking about, every day we're trending towards that about 3 billion events ingested into this system. And we're serving up and down, but around 5,000 queries a second, fetching metrics and analytics from this cluster. Patrick talked about similar topology that his data, the segmentation data store is built off of. Apparently, this is the second largest ClickHouse cluster at Klaviyo. I learned that tonight. But the topology here, right, why we have these logical layers on top of physical data shards, right, is for compute isolation, right? It scales out ingestion because ingestion sort of by event type gets written deterministically to the same place. And then it gives you isolated read workloads in a deterministic way as well. So it's kind of core sharding mechanism sets us up for a little bit better scale. In terms of what that data actually looks like and what those read workloads look like, you can see that about 75% of the queries that we get scan the last 30 days or so. Basically, typically most of it is within the last week, and then you round up to the last month. So you imagine the sort of physical schema that lives under there, right? Partitioning by time, partition by month, right? You're targeting this hot data set. And then again, you think about the use cases we're supporting, very message-centric. And so about 85% of our queries are looking to group or filter by message-related dimensions. The other thing that's, I think, helpful to think about when you look at the sort of mix of workloads that we're running, calls into these services come from a couple hundred different places. And when I say that, what I mean is different call sites tagged with basically by the use case and by the usage for how they're generating their queries. And what you want to think about there is that they all come in at different rates. They all have different SLOs. And when you're thinking about an offline report generation in a task queue somewhere that can fail 6 times and not make anybody upset because it's just done the next morning, right? Like that's a very different failure mode than a UI that won't load or an API call that's less responsive. So we're trying to juggle a pretty big mix of different kinds of use cases. And when that goes well, it's great. But then sometimes it doesn't go well. So this is the core of the story that we want to kind of tell, right? These big heterogeneous workloads, we want to support in a really efficient way. But when we introduce the service, every once in a while, we'd see these bottlenecks. And the difference between, you know, P95 of 100 milliseconds and, oh no, this giant wave of timeouts from our caller's perspective really sucks. And it's really hard to go to your coworkers and say, hey, what's up with your service? I am not doing anything different. This is the same calls I made yesterday, and now I'm just hitting timeout after timeout after timeout. So I want to talk about a layer that we put in front of ClickHouse to react to and respond to and control the traffic so that we can keep chugging along with this query engine really efficiently and manage really different query loads from tons of different callers and still have everything up and running. Does that make sense? Yeah. Okay, so let's break down a little bit of the request flow here. Helps get a picture. So all the way on the side, we have the callers, right? They're all calling in, they're identifying who they are, and then calling in, terminate the request in an envoy layer that fans out the traffic. And we're going to zoom in on the metric service server pods here to talk about this cluster and how we handle the workload. That's fronting the ClickHouse cluster. When I gave this talk in California, there were 2 other talks about metric service systems at companies that were also failure stories. So I don't know how to, I think the takeaway is don't call your service metric service. But we're in good company. So the service itself is running Python gRPC servers. And what's important about that detail here of how we're fronting the service, there's a lot on the diagram, but what's important to think about is that we get for each of the pods that's executing all these different query workloads, we get a single entry point, and then work gets passed on to worker threads that are actually the ones grabbing the database connections, talking to ClickHouse, getting the results back, doing some post-processing. But we have a single entry point, and that becomes important for how we learn how to control and shape the traffic. When we put this system in place, one of the sources of inspiration was a great blog post by Netflix, and they open sourced their library for concurrency control. We adapted it to this situation, but this definition, I think, is really useful here, right? So when we're thinking about controlling the traffic, we're thinking about managing concurrency. What they say is concurrency is nothing more than the number of requests a system can service at any given time. And it's normally driven by a fixed resource, such as CPU. So in that wall of timeouts, like what was the fixed resource we were hitting? Where was that contention? A system's concurrency is normally calculated using Little's law, which states for a system at steady state, concurrency is the product of the average service time and the average service rate. Any request in excess of this concurrency cannot immediately be serviced it must be queued or rejected. And we were not immediately servicing these requests. They were queued and they were timing out. With that said, some queuing is necessary as it enables full system utilization in spite of non-uniform request arrival and service time. Systems fail, this was the painful part to read, when no limit is enforced on this queue, such as during prolonged periods of time where the arrival rate exceeds the exit rate. As the queue grows, so will latency until all requests start timing out, and the system will ultimately run out of memory and crash. If left unchecked, latency increases start adversely affecting its callers, leading to cascading failures throughout the system. You can imagine like the point in that debugging process where we read this, we're at our lowest, but if we can figure this out, how to copy this and re-implement this, there's a ray of hope. So that's a lot of words, but it comes down to this question. At the front door of your system, should you take on more work or should you reject it? Because if you don't have this rejection mechanism in place, you get this queuing problem. You get this timeout problem. And I'll talk about how concurrency control here is a little bit different than what we can sort of have in ClickHouse. So here's the super simplified diagram of what Netflix is talking about. If we have a request queue and we have 3 requests in our queue, and each of them have given us 4 seconds to process. Right? They come with a deadline. And we know our service is there processing 1 request per second. Should we take on 1 more request into this system? Yeah, we'll get there. We're just gonna make the deadline, right? Because we'll chug along and process those 3, and we'll get to the 4th one before it times out, before the deadline. However, right, if another one comes along, we wanna know before we put it in the queue whether we think we have time to process it. And in this case, the answer is no. So the conjecture here is that it's better to reject it outright than have it die in the queue. So that's what we try to do. Now, this can happen locally on every node in a cluster without any coordination, which is kind of cool because it sets up this dynamic. And I know this is a little bit tricky to read, but here's what I want you to see here. If we send in a new request and it hits that server at the top, that first server knows it doesn't have capacity to take on new work. So it's going to reject the request. But there's an entire cluster of servers available. So our mechanism here between the client and server, we can immediately try again. And it becomes effectively, the early rejection becomes a routing mechanism because we can seek to a server that does have capacity. So this is, I'll show you a chart in a minute. This is what we actually observed in practice, that while we were like controlling for overload locally, when you blow out, zoom out to the entire cluster, we actually have now a balancing mechanism for finding capacity in the system. There's another layer to this, an adaptive layer, which deserves a lot more sort of explanation that we don't quite have time for tonight. But in this adaptive layer, the difference here is that a static concurrency control system, kind of like setting max concurrent requests in a database, is good for half of the problem. It's good when there's an influx of work to be done that exceeds the capacity of the system, right? So a static limit is kind of like a ceiling. But what it doesn't do is it doesn't react to changes in the downstream, any downstream dependency of that system. So if I get slow for whatever reason, and I still think I can take on 100 requests at a time, all of a sudden I'm gonna hit contention again. So the piece here, right, an adaptive mechanism, which is effectively a feedback loop, right, allows us to basically track how long work is taking. So it's now, this is the other half of Little's law, it's the service rate and the service time that we're both taking into account, not strictly the number of requests as a static number that we work on at any given time. So again, we could go into it in a lot more detail, but in our single threaded entry point to that Python gRPC server, we can now start the clock when we submit the work to be done. And I don't have to know how complex my query is. Don't have to do any parsing. I don't have to know the state of the query processing service that's doing query planning, doing routing to the right database, doing any of the post-processing. And I don't have to know anything about the state of my database behind it. I don't have to know if all the nodes in the cluster are up or down, who's available, right? I don't have to make any fancy guesses estimating the query cost and complexity, because when that query comes back out, I'm going to measure how long it took. I'm going to track all my observations of how long we do it actually over like a 3-second window, right? We accumulate a few hundred requests locally and say, this is how long on average, or this is how long my P95 latency is of the last 500 requests I've observed. Right now, can I keep up at the speed, the rate that I've set for my system, I've calibrated it to? If I can, great, keep work coming. If I can't, I need to do less work, with the idea that eventually I'll speed back up again. So measuring latency and recalculating the current capacity in the system solves for everything downstream of accepting the request. And you don't have to get into anything complicated. The last thing about it, skip a couple of details here. The last thing about it is the answer now to my workload hasn't changed. Why are my queries timing out? We have a much better answer, because this can work as overload protection in your database, but it can also work as a policy layer for your callers. I can now, there's a partitioning mechanism inside the capacity calculation. I can now reserve capacity for certain callers or groups of callers, so that even if I'm in an overloaded state and I'm shedding load and dialing back how much work I decide the system can do, I can still have a floor to that reserves query processing capacity. So for us, that meant I get a storm of requests from a public API now that starts knocking over the database because the queries are way more complicated than we anticipated. Somebody loading a dashboard in a UI never has to know about that, never is disturbed by that. I've got, by this reserve capacity, I've got much cleaner workload isolation, independently to a degree of the state of my database. So that was a lot of theory that we worked with for a long time. And this is what we saw when we put it live. So here's a chart where my round trip times are increasing. All of a sudden, my overall round trip time, RTT, has gone from 100 milliseconds to 400 milliseconds. I expect to see, as a result, lockdown. My limit, how many queries I'm allowed to process right now, drops in response. Yes, it worked. Stop doing as much work. And notice the limit goes back up. Same thing on the latency on the other side. Latency will go back down as I reduce the amount of work in flight. And so what you end up seeing, you basically can configure an SLO for the system, right? You can say, I want 95% of my queries to process within 200 milliseconds. If you set that at the concurrency controller, then you're going to see this kind of sawtooth pattern that sort of seeks to that number, because you're letting more work in as you go up and up and up. As soon as you go over that limit, we're going to see this drop in the limit, and the response times will go back up as the limit goes down. And then the coolest part of this to see live was the cluster behavior that we talked about. The latency wasn't evenly distributed, right? So some of the servers were spiking, some of the other ones were chugging along. And that's just because the mix of query workloads throughout the cluster for all those different use cases we talked about lands in different places at different times, and you don't have to do anything fancy to try to anticipate that. You're basically rebalancing the work in response to however it tends to land in your system. So you can take the hands off the wheel, this thing steers itself as you get your mix. And then when things did go bad and there were downstream bottlenecks or things we couldn't control, it's not this giant wall of timeouts for everybody anymore. We've created better workload isolation. You may have latency spikes as we've onboarded more complex use cases, right, that are closer to these sort of like ad hoc, more sophisticated queries people will run. Expected latency goes up, but we don't have to penalize the entire cluster, all the users, because we have better workload query isolation at the service in front of the database. That took 3 hours the last time I did it. Awesome. Thank you. Thank you. Yes, sir. Yeah, it's kind of interesting. It doesn't tend to be that much of a problem when a new server comes up, or because most of these windows are pretty tight, and we never let it get too far out of configure it to have kind of like, you're not configuring it all the way open, kind of half open to start. So you don't sort of let the throttle all the way open. But again, with the query volume we're seeing and the sort of number of queries we need to run through it to start to get our window, it seeks pretty quickly. And then you can also tune the sort of back off factor when you do scale the limit in. So if you found that that was consistently a problem, you could put a more aggressive back off factor into your limit controller. Yeah. What's that? Yeah, yeah, yeah. Yes, sir. Yeah. Yeah. So we're considering 3 as well. They've convinced us. No, but so in the way we use the distributed tables to resolve queries, in that topology, right, you've got sort of large logical sharding to sort of cleanly separate workloads, but within, so we have 8 nodes running per layer, right? There's 4 physical shards. So when you write data, you're round robining your writes. You're not really, you're sharding the writes. So with those replicas, to answer a distributed query, either one can participate. And so one way to think about it is, if you're okay with the storage, replicas there give you more QPS, more throughput in the system. Because now, in this current setup, one of those 2 replicas has to participate in every query, right? So it goes to a logical layer. We need to recruit 4 out of 8 to participate and fetch the data, regardless of who's sort of the orchestrator for that. So adding another replica then gives you more throughput, sort of more concurrent throughput that way, is one benefit. Yeah. Yes. Yeah. So there's layers to it, which is really interesting, because often the overload's very ephemeral. And so with the client server mechanism that we had in place, we would be, if we were in an overload condition, we would throw back a retriable error to distinguish it from some other failure. And even before it propagates back up to the caller, we're retrying within the client server on a tighter loop. And so most of the time, these don't come all the way back up. The second layer, the second piece of that is that when we are the sort of concurrency control, and it can act as a policy layer where we're deciding who gets what allocation. So to reserve extra capacity so that our dashboards have more reserve than a public API that expects throttling or something like that. Yeah. But we try to minimize the hits. Yeah. Yeah. Scaling the database cluster with terabyte volumes attached to it. It can't be responsive in the same way, right? Yeah. And I think you want to look at the scaling considerations in terms of responsiveness, though, and then in terms of planning, and we're also trying to play with more help with using object store backing, and tiers. So give us more compute scalability, which we think we can isolate. I'd be curious if anybody's played with this. Isolate our sort of data serving nodes from our compute layer, and gives us that decoupling and that scaling. Something we're going to be looking into this year. So yeah, I think there are a lot of axes to play with. Cool. Thanks, everybody. Appreciate it.